Hello everybody, welcome back. Today we are going to be talking about properties of exponents and radicals. We have two learning objectives. The first is to use properties of exponents to solve problems, and the second is to use properties of radicals to solve problems. Now we're going to learn the properties of exponents and we're going to learn the properties of radicals in this video, so you don't have to know those going in or anything like that. This is also going to be one of those videos that I'm going to go through steps a little bit slower just to make sure that you guys have what you need. So if this is moving a little slowly for you, either speed me up, right, or you can just kind of skip to the parts that you think you need, that sort of thing. All right. Now let's go and jump into it. So first of all, we're going to learn the rules of exponents, right? We're going to use properties of exponents to solve problems. We need to know what those rules are, the properties are, in order to make it work. So rules of exponents, we have a few. So the first is called the product rule. And the product rule is pretty simple. If we multiply the bases, then we add the exponents, right? As long as the bases are the same, if we multiply a to the m times a to the n, this is the same as a to the m plus n. So to give you an example, if I have 4 to the 2/5 times 4 to the 1/5, this is the same as 4 to the 2/5 plus 1/5, which is just 4 to the 3/5. And this is a simplified version of both of these things being multiplied together, right? The base stays the same, you add the exponents together. Pretty simple. All right, the quotient rule. The quotient rule is very similar, right? Before it was if we multiply, we add. This one is if we divide, we subtract. That's always kind of the mindset I like to get people into, because especially when we get into the next unit, we start talking about logs, you're going to want to know that relationship between adding and multiplying and subtracting and dividing, right? So, quotient rule, we have a to the m over a to the n, and that's going to equal a to the m minus n. So for a good example for this, if we have 3 to the 4th power, and 3 to the 2nd power, 3 squared, 3 to the 4th over 3 squared is going to be 3 to the 4 minus 2, which is just 3 to the 2, which is just 3 squared, which is 9. All right, and now we have the power of a power rule, which in other words is a to the m, all of that to the quantity raised to the n, right? So a to the m to the n, the whole thing raised to the n. This is the same as a to the m times n. You're just multiplying the exponent. If it's m to the n, it's kind of like the n is being distributed to the n. It's a good way of looking at it. So this is a to the m times n. So if we have 7 to the 3rd power, and then all of that to the 2/3, this is the same as multiplying this 3 and this 2/3. So 7 to the 3 times 2/3, which 3 times 2 is 6, 6 over 3, right? So 7 to the 6/3. 6/3 is the same as 2, so 7 squared, which is 49. All right, power of a product rule. Now what this says is if we have two numbers being multiplied together, in this case they're variables, but if we have two numbers, a and b, and all of that is raised to the m power, that's the same as a to the m and b to the m, right? A to the m times b to the m. You're just taking both of the numbers inside, and it's like you're distributing this m to both of these, right? If you want to look at it that way. All right, so we have 16x to the 1/2, the quantity 16x raised to the 1/2, which is going to give us 16 to the 1/2, right, times x to the 1/2. It's distributing this 1/2 to both. And that's going to give us 16x, right? Because, well, the square root of 16x, all of it, right? And then we know 16 is 4. So we can bring the 4 out. So it'll give us 4 to the square root of x. And we'll talk about that rule a little bit later. All right, negative exponent rule. We have a to the negative m, and that's going to equal 1 over a to the m. So anytime we have a negative exponent, we can actually put it in the denominator, and it'll turn the exponent positive. So if we have 5 to the negative 1/2, this is the same as 1 over 5 to the positive 1/2, which in this case 5 to the 1/2 is the same as the square root of 5. You should try to leave the answer in the same way that it started. So if this has a rational exponent, you should leave it the rational exponent. So this second answer is probably more precise. I just wrote this out just to make sure that we're kind of reviewing from the last lesson a little bit. All right, use rules of exponents. Here we go. So now we're going to do some problems together. All right, and we're just going to use the rules we just talked about. So this first one, we have 81 to the 5/6 times 81 to the negative 1/3. This looks a lot like if we are our product rule here, right? If we're multiplying exponents, we're actually just adding, or if we're multiplying numbers with the same base, we're just adding the exponents, right? So let's go ahead and do that. So we have 81. And then we're adding these exponents, remember? So 5/6, and then this is plus a negative, which is the same thing as minus, right? Plus negative 1/3. So it's actually going to be minus. And if this is 1/3, we need the denominators to be the same, right? So it's just going to be minus 1/3 is the same thing as 2/6, right? So I'm just going to kind of do this real quick. This is just adding fractions at this point, right? So 5/6 minus 2/6 is going to equal 3/6. So this is going to equal 81 and 3/6. 3/6 is the same as 1/2. You should always reduce if possible. So 81 to the 1/2. And this is how we're going to leave it, because in the beginning our problem used rational exponents, so we're going to end with rational exponents. It's usually a good rule of thumb. All right, so the next one, we have xy to the third over x to the 1/2, all of that to the 2/3. All right, so first thing, we have a couple rules here. First of all, I see division, right? So I see x to the first. We can just kind of look at this as, this is like x to the first, right? So we have x to the first divided by x to the 1/2. When we divide the same base, we're actually subtracting the exponents. So let's go ahead and do that part first. We can view this as all as one step, but I'm just going to write this out first. So we have x to the 1 minus 1/2, right? We have the 1 on top, the 1/2 on the bottom, so that's what the x is going to be. And then y is just y to the third. So we don't really have anything going on with that. But remember, this whole thing is raised to the 2/3. So all of this to the 2/3. Let's go ahead and simplify the x real quick. Okay, so this equals this. So let's go ahead and simplify these x's. We have 1 minus 1/2. If I have a whole pizza and I eat half of it, I only have half of it left, right? So we have x to the 1/2, y to the third, and all of this is to the 2/3. All right. Now remember, this 2/3, it kind of distributes to both of these, right? This is when we go back here to the power of a product rule. If we have any number raised to an exponent, or two numbers multiplied together raised to an exponent, it's as if that exponent is being applied to both. So this 2/3 is going to be applied to both. So let's go and multiply those out. So this is going to equal, well, we have x to the 1/2 times 2/3. 1 times 2 is 2. So x, 2, and then 2 times 3 is 6. So x to the 2/6, which is going to be a third. We'll reduce that in the next step, okay? And then y to the third to the 2/3 is going to be y, 3 times 2 is 6, over 3. All right, last step is just to reduce these. So we have x to the 1/3, y to the 2, right? Y squared. And that's it. That's all we can do, right? But we broke this down quite a bit. I mean, if we look at our original problem and then we look at our answer looks a lot better, right? This is a jumbled mess. This is very clean. All right, perfect. Now, last one is this, try it down here, right? 2a to the 1/3 times ab to the 1/2, and then that whole quantity in there is raised to the 2/3. Go ahead and give this one a shot. Pause the video, and I'll get back with you here in a second. All right, so let's go and give it a shot. So we have 2a to the 1/3, ab to the 1/2, and then ab to the 1/2 is all raised to the 2/3. Let's start off with this other part, right? Because, I mean, we could multiply these two together. We could do that if you wanted to. I'm just going to go ahead and let's distribute this 2/3 to both, right? So I'm going to leave this part the same. So we're just going to leave the 2a to the 1/3. We're just going to leave that for now. We'll get back to that later. And we're going to distribute this 2/3. So this is going to be a to the 2/3, right? And then b to the 1/2 times 2/3 is 2 over 6, which is the same as 1 over 3. Okay. Now, we're multiplying these together. When you multiply numbers, or when you multiply exponents with the same base, you just add the exponents. So this is going to equal, the 2 is just going to kind of stay here, right? The a is going to be a to the 1/3 plus 2/3. And then the b is just b to the 1/3, right? Okay. Now, again, 2 just kind of is doing its own thing. Now, a to the 1/3 plus 2/3 is just a to the 1, right? And a to the 1 is just a. So that's kind of nice. And then b to the 1/3, there's nothing happening to that. So that's it. That's as clean as we can make this. But that looks a lot better than all this up here, right? Okay. Cool. So that's it. We just used rules of exponents to solve problems, right? We didn't get into any word problems or anything crazy like that. We'll do that later. But for now, we're just kind of practicing the more complex algebra, okay? All right, now, Now we're going to need the properties of radicals, right? Because we eventually want to use properties of radicals to solve problems. So we need to know what those properties of radicals are. All right, so here we go. And these are kind of just a breakdown. These aren't as much rules as the last ones were, but these are more just how these work. So, all right, the product property is if we have the nth root of a times b, this is the same thing as the nth root of a times the nth root of b, right? So in other words, the ab can be separated. All right, and then it can go the other way, right? If we have like the square root of 2 times the square root of 4, it's the same thing as the square root of 8, right? We can just multiply those together. That's fine. And then the same thing, of course, applies to the rational version, the rational exponent version. So if we have ab to the 1 over n, right? Remember, these two things are the same, right? This thing up here and this thing here are the same. But it's the same rule. So ab to the 1 over n is a to the 1 over n times b to the 1 over n. Okay. And then, of course, you can put it back the other way, too. All right, now quotient property is the same idea. If we have the nth root of a over b, that's equal to the nth root of a over the nth root of b. And then if we have a over b to the 1 over n, we can say that that's a to the 1 over n over b to the 1 over n, right? We can break these down. It's if the negative is distributing, or it's as if the exponent is distributing to both, or in this case, the root is distributing to both, right? It's the same concept. Now, anytime we're simplifying things with radicals, there's two real rules, okay? First of all, we have to take all of the perfect nths that we can. In other words, if we're dealing with square roots, we have to take all of the perfect squares. If we're dealing with cube roots, we have to take all the perfect cubes out that we can, right? We always have to reduce that as much as possible by removing everything we can. And then finally, we can't have radicals in the denominator. That's the other rule, okay? I'm going to show you how to deal with both. So let's go ahead and start by removing perfect nths. So let's do it. Let's start with an easy one, okay? So simplify the square root of 18. Hopefully you know how to do this. If not, that's why we're here. So in a square root, right, n equals 2. So the perfect nth in this case is a perfect square, right, because that's what it means. So we need to remove all of the perfect squares we can. Now I'm going to give you a little table with perfect squares here. 1 squared is 2, 2 squared is 4, 3 squared is 9, so forth. Now, honestly, in these situations, the 1 squared is 1 isn't really going to help us too much, but it's technically part of the list, right? Because we're not going to pull out ones, right? That's not going to do anything for us. If we take 18 divided by 1, divided by 1, divided by 1, we're not getting anywhere, right? But let's perfect square hunting, okay? This is a phrase that Mr. Kowalski actually taught me that I thought was really cool. And let's go and do this. So perfect square hunting is find the perfect squares, right? So if we take 18 and we break down what the factors of it are, well, 18 is either 1 times 18, it's 2 times 9, or it's 3 times 6. Now, there's only one perfect square in here, well, besides the 1, right? 1's always a perfect square. But besides the 1, we only have one perfect square, and it's this 9, right? So we're going to use this 2 times 9 to break apart the square root of 18, right? So if we do this, so the square root of 18 is going to equal the square root of 9 times the square root of 2, right? Remember it said back here that we could do this, right? That's this first rule up here, but we're going from here back to here, right? That's kind of what we're doing. So the square root of 18 equals the square root of 9 times the square root of 2. And the square root of 9 we know is 3. So this is 3 times the square root of 2, which gives us our final answer. So the square root of 18 should be simplified into 3 times the square root of 2 in order to be fully simplified, right? Now that's cool for perfect squares, right? But what if it's not a perfect square? What if n doesn't equal 2, right? Well, let's simplify the cube root of 16. Now in this case, n equals 3, right? This is the cube root. So we need to find perfect cubes. We're going to go perfect cube hunting in this case, right? So the perfect cubes, I went ahead and listed these off for you here. Cube root, or 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, and so forth, right? And you'll notice I keep putting this at the end with the x cubed is x, because that's the number that we can, I guess it would kind of work the opposite way, right? X and then x cubed. But you could, if you have 3 x's, you could take out an x, is the idea, okay? All right, so let's go ahead and do this. So the cube root of 16, let's find the factors of 16, just like we did before, right? We have 1 times 16, 2 times 8, and 4 times 4. Only one of these is a perfect cube, well, besides 1, right? And it's 8. 8 is our perfect cube, so we're going to use this 2 times 8 to break apart our radical here. So 16 is going to become the cube root of 8 times the cube root of 2, right? And we know the cube root of 8 is 2. That was the whole point. So this is going to be 2 times the square root of 2, or the cube root of 2. All right, perfect. Now, this is just a note, okay? I strongly encourage you to, after I say this, pause the video and kind of do what I'm about to tell you. You need to know the perfect nths. Okay, if I were you, I would just in your notebook come up with a list starting now. Okay, now I gave you the perfect squares, right? They're right up here, and I gave you the perfect cubes. You need to know the perfect fourths and the perfect fifths. Okay, probably a little bit more. Maybe know like 1, 2, and 3 for the sixths or things like that, right? The more you know these, the faster you're going to be at these problems. Think of it as like times tables, right? This is the times tables of this unit. You really need to know these things, or at least have them written down so you can reference them quickly. Okay. All right. So we had two rules, right? The first rule was we need to take out all the perfect nths. That's what we just kind of learned how to do. Now we're going to remove a radical in the denominator. Now, let's go ahead and simplify 2 over the square root of 2. Now, obviously we have a radical in the denominator, otherwise this would be fully simplified, right? So, you'll notice that the square root of 2 is a square root. So we need to make the denominator a perfect square. Now, fortunately for square roots, it's pretty simple. If you multiply something by itself, it'll always create a perfect square, right? Because that's just how square roots work. It's a number times itself, right? That's how squares work. So, in this case, we can just multiply both sides by the square root of 2. But you could really multiply it by any square root so long as it makes a perfect square, right? In other words, if we have the square root of 2 on the bottom, and I want to turn this into, what's another perfect square? 16, right? I could multiply it by 8. That would work. We'd get the square root of 16 on the bottom, right? And then that would end up being a 4. We'd have to reduce it more at the end, right? But you could do it. It would work. So we need to make a perfect square. Now you'll notice that what we do is we're going to multiply the bottom by the thing that we need. So square root of 2 times the square root of 2 is going to give us 4, right? So that's why we do this. And as long as we multiply the top and bottom by the same number, we aren't changing anything, right? Because this just equals 1. All right, so we're going to multiply the top and bottom by the square root of 2. And if you'll notice down here, we'll kind of go through this, but you'll see the reason is that square root of 2 times the square root of 2 is going to give us the square root of 4, which is a number, right? So it's going to eliminate the radical from the denominator. So 2 times the square root of 2, that's what we have up top. Square root of 2 times the square root of 2 becomes the square root of 4. So now we have the square root of 2, or 2 times the square root of 2 over the square root of 4, which becomes 2 times the square root of 2 over 2. These 2's will cancel, right? And you'll be left just with the square root of 2. So, I mean, we not only got rid of the square root in this case, we got rid of the entire denominator, which I guess is kind of nice. But that's what happens, right? Is we are going to turn this denominator into a perfect square. In this case, square root of 2 times itself works, right? Perfect. So what if the denominator is a binomial? Well, if that's the case, then we need to use the conjugate, right? We need to multiply by the conjugate. So the conjugate of 2 plus the square root of 5 is 2 minus the square root of 5. So if we simplify this, we're going to multiply the numerator and denominator by 2 minus the square root of 5, right? So let's go ahead and show you what that looks like. So remember, the conjugate is just the opposite operation. So let's do it. So we have 1 over 2 plus the square root of 5, and we're going to multiply this by the conjugate, top and bottom. So 1 times 2 minus the square root of 5, 2 plus the square root of 5 times 2 minus the square root of 5, right? So we're going to FOIL these. So first of all, up top, this is just 1 times this, so it stays itself. Now on the bottom, we're going to have 2 times 2, right? 2 times 2 is 4. We have 2 times the negative square root of 5, which is going to be negative 2 times the square root of 5. We have the square root of 5 times 2, which is 2 times the square root of 5. And then we have the square root of 5 times the negative square root of 5, which is the negative square root of 25, right? 5. So just like when we did I, right? Remember, we actually did this trick when we were dealing with I before in quadratics. You'll notice that the 2 to the square root of 5 and the negative 2 to the square root of 5 cancel out. So that's how we're getting rid of the square roots in this case, right? And then this square root is going to eliminate because it's a perfect square. So we'll have 2 minus the square root of 5 over 4 minus the square root of 25, right? Which gives us 2 minus the square root of 5 over 4 minus 5. 4 minus 5 is just negative 1. And this is pretty simplified, but we can get rid of this negative 1, right? If we multiply the top and bottom by negative 1, it'll eliminate this. So that's all I did here. Because negative 1 is going to cancel out, right? And then negative 1 times this is just going to flip the signs. So negative 2, and then negative 1 times negative square root of 5 is just positive square root of 5. So this is actually our final answer. And if we look at the original problem, we simplified this into this using the conjugate. All right. So that's the trick for if it's a binomial, right? If it's multiple pieces. Remember, if it's a single piece, you need to think about what it is. So in this case, it's a square root, right? So we need to make the bottom a perfect square. If it's not a square root, we'd have to make it something different, right? So if it was a cube root, we'd make the bottom a perfect cube, right? That sort of thing. All right, so let's go and try a few examples here, okay? I'm going to do one with you, and then I want you guys to try the next two, and then we'll jump into it together, okay? All right, so let's go and do this one. So using the property of radicals, remember there's two rules. We can't have any radicals in the denominator, which is what we just learned, and we have to take out as much as possible. In this case, we have a cube root, so we need to take as many perfect cubes out as possible. All right, so I'm going to just do each of these parts individually, okay? So let's think about 16. What's a perfect cube we can take out of 16? That multiplies into 16, right? If we go down to this list here, we have 1 and 8 and 27, right? 8 will work, right? Because 16 is 2 times 8. So let's do that. So this is going to be, let's do our 16 first. Our 16 is going to break down into 2 times 8, right? And I'm going to break that down even more into 2 times the cube root of 2. Because if we can get everything to just have a little 3 above it, right, an exponent of 3, that'll help us with this problem, okay? So let's do x to the 5th. How can we break down x to the 5th? Well, exponents are actually a little bit easier when they're on variables, right? Because this is simply x to the 3rd, right, times x squared. We did it. We got the x to the 3rd, right? It wasn't anything crazy. So now what we're going to do with these answers, right? We have this and we have this. Now what we're going to do is we're going to take our cube root. This is in my opinion the easiest way to think about it. And any perfect cube we have, we can actually pull that out, right? So here we have a perfect cube of 2, so we can pull a 2 out, right? And here we have a perfect cube of x, so I can take an x out, right? And then anything that we don't have up to a perfect cube, we have to leave inside. So here we have a 2x squared. That has to stay on the inside. That's it. That's the answer, right? We took out as many perfect cubes as possible. And not only that, but we don't have any square roots in or cubed roots or any roots in the denominator, so we're good. All right, so go ahead and try these, okay? These two are going to do completely different things, okay? I'll kind of give you a hint. This first one is going to be much like the one we just did, where you're going to just take out as many perfect fourths as possible, okay? Hopefully you made that list, because 81 is the special number, and you'll see what I'm talking about. Now, in this bottom one, you'll notice this is a cube root, right? So you're going to have to use a rule to turn this into multiple roots. And then remember that we need to make the denominator a perfect cube, right? So you don't just multiply it by itself, you multiply it by what's necessary to make it a perfect cube. That's a bit of a hint. So go ahead and pause the video, and here in a second we'll jump back into it together after you've tried. All right, I went and took a nap and came back, so now let's go ahead and work on this together here. So I told you this one was going to be like the one before. We want to go perfect fourth hunting in this case, right? So let's go and break this down. I'm going to do each piece individually. 81, a to the 8th, b to the 5th. So 81, hopefully you saw on your list that 81 was actually just 3 to the 4th power, because that's what we're just going to leave it as, because we want as many things to the 4th power as possible, right? Well, if we can break down the 81 perfectly, let's just do that. So 81 is 3 to the 4th. A to the 8th, we can break this down into a to the 4th times a to the 4th. And in this case, we got 2 of them, right? Now, if this was like a to the 9th, it would just be a to the 4th times a to the 4th times a, right? You take as many a to the 4th out as possible. And then b to the 5th, it's kind of the same idea as what I was just saying, right? This is b to the 4th times b. Now, everything that's to the 4th power, we can pull on the outside. So there's going to be a lot more going outside than staying in this case. So this is the 4th root. What can come out? Well, it looks like a 3 can come out. It looks like an a can come out. Looks like another a can come out, right? We're eliminating these as we go. And then a b can come out. And on the inside, all we have left is this b. Now, we can simplify this a little more, right? Because a times a is just a squared. So this is going to be 3a squared b times the 4th root of b. That's it. Hopefully you got here. If you did, are there any roots in the denominator? No, there's no denominator, so that's probably good. And then, yeah, if you look inside the radical, is there anything that you could take to the fourth power? Well, of course not, right? It's just a b. So, yeah, we did it. All right, last one. This one's a little tricky, so if you didn't get this one, that's fine, right? Now, hopefully you found this first step, right? Because if we go back up here to our rules, right, all the way back here, we said that n to the a over b is the same as n to the a over n to the b, right? So if we go back here, this is the cube root of 2n over 9m. So that's what we're going to do, is rewrite this the way that that rule just told us we could, right? So this is the cube root of 2n over the cube root of 9m. Okay, now before I told you that we have to make this bottom a perfect cube, right? That was the hint I gave you. Well, what can we turn this into to make it a perfect cube? Well, I know 27 is a perfect cube, right? And I know 3 times 9 is 27. So I'm just going to we can just write this anyway, right? Just kind of give us a hint. So I want to multiply this by 3. And then this m, what do I have to make the m to make it a perfect cube? Well, I need to multiply it by another m squared. So this here, this little thing here, is what I want to multiply the top and bottom by. Because if I can multiply the top and bottom by this, I'm going to get rid of the denominator. So I'm going to multiply the top by the cube root of 3m squared, and I'm going to multiply the bottom by the cube root of 3m squared. Right? And I'm literally just multiplying across here. Right? This is the same thing as multiplying by 1, the same on top and bottom. And that's going to give me 2n times 3m squared. So 3, or the cube root I should say, of 6n m squared. Right? And just, that's all. Can't really simplify it more than that. And then over, and this is what's really cool, 9 times 3 is 27. So the cube root of 27 m to the third. Now, the whole point of this was to make this as many perfect cubes as possible, right? So if we just take this bottom one, let's just take this bottom piece and simplify it real quick, right? Okay, so 27 is the same as 3 to the third, right? So we broke that one down, and then m to the third can be broken down as just m to the third, right? It's not really, right? That's just it. So we can take out a 3, we can take out an m, right? That's the idea. So if we take out a 3m, then we're going to get this to equal, the top is going to be the cube root of 6n m squared. And then the bottom, right? We're taking everything outside, right? We're taking the 3 out, and we're taking the m out, right? The 3 and the m both get taken out, so there's no more square root on the bottom, or cube root, which is the entire point, right? Now, this is fully simplified, right? Is there any cube up top we can take out? Well, no, right? And is there any denominator that has a root? And there isn't. So we are done. All right, one more. We can do it. All right, application problem here. Let's see if we can do this. So a high school drama department is designing a set for an upcoming musical. The image below shows the wood needed for the bracing on the back. So there's wood here, and this is the stuff that holds up the wood. Assuming the set is made up of 2 square boards, will 75 feet of wood be enough for the bracing? Okay, well, there's not really a lot to do to this other than just kind of add stuff together, right? So let's just make some markings here of things we know, right? We know this part's going to be 4 because we're assuming that these are squares, right? So this is a 4, this is a 4, this is a 7, this is a 7, this whole bottom piece is an 11, right? And then, well, let's do these diagonal boards last, but this little piece here is also going to be a 4, right? This one up and down. Okay, so really what we could do this as is we can say this is 4 times 4, right? Plus, what, 3 times 7? Does that make sense? Yeah, we have 4 squares here, 4, and then there's 3 of these 7s. So this is going to be 16 plus 21, which is going to give us 37. So we're going to start off with 37 feet, okay? And that's 37 feet before we get to these diagonals. So how do we do the diagonals? Well, let's see if you remember a little bit of geometry. Fortunately, I know a geometry teacher. He's pretty good at it. So he taught me this really cool trick. And basically what it is if we know that this length is 4, right, and we know that this length is 4, this is a right triangle, it's also an isosceles triangle. If something's a right triangle and an isosceles triangle, it's also known as a, drum roll please, 45, 45, 90 triangle. This is amazing. Okay, so anytime you have a 45, 45, 90 triangle, the hypotenuse is the side times the square root of 2. And both of these are going to be this, right? So in this case, it's going to be 7 square root of 2. And over here, it's going to be 4 square root of 2. If you didn't remember that kind of really cool rule using 45, 45, 90 triangles, just use Pythagorean theorem, right? The square root of 16 plus 16, which is 32. Square root of 32 is going to be what? 4, 16, right? Times the square root of 2. So it works out. All right, anyway. So we have 45, 45, 90 triangles. So we know we need to add these pieces. So we're going to add a piece of wood that's 7 times the square root of 2. And we're going to add a piece of wood that's 4 times the square root of 2. Now, the only way to find these numbers is just to multiply them together, right? There's not any like crazy math. But let me show you a trick, okay? And it's just to make sure that we understand this. If I had 7x plus 7 or plus 4x, right? What we would do is we would just say this is 11x. And I want you to think of radicals the same way, right? As long as they're both the same power, in this case, this is like a square root, right? It's like a little 2, and this is a square root. So this would be like saying 7x squared. We can add these together, right? 7 and 4x squared. That works. Now, and if the number on the inside is the same, right? This is a 2 and this is a 2. If either of these were a 3, it would be like adding an x and a y. We can't do that either. So as long as these are exactly the same, which in this case they are, we can just add the numbers. So it's like 7 of these plus 4 of these is just 11 of these, just like down here. So this all equals 11 times the square root of 2. Okay? When you add terms, remember they have to be like terms. In this case, they're known as like radicals, and that the degrees are the same, the power is the same, and the actual number on the inside is the same. Okay. So in order to find 11 times the square root of 2, we just need a calculator, right? Or if you know some other trick, you can use that. But let's go ahead and do square root of 2, which is 1.414, whatever. We're multiplying that by 11. So let's just do that. And we get 15.55. Let's just round it to 15.56, even though we're going to the nearest foot, so the rounding doesn't really matter. But 15.56, let's just say that. So we're going to actually, over here, we have 37 feet. This is 15.56 feet. And we can add those two together, and that'll be all the wood we have. So 37 plus 15.5, 37, I just don't feel like doing the math right now, 52.56. Even I, when I get 40 minutes into a video, get a little tired, so. All right, 52.56 feet. In other words, to answer the question, is 75 feet of wood going to be enough? Yeah, it is. All right, perfect. That's it. That's the problem, right? It kind of showed us how to add these together. Let us use a little bit of geometry. Technically, there's radicals, so it works, right? All right, cool. If you have any questions, let me know. There's a couple things that you're going to want to do from this lesson, okay? First of all, you're going to really just want to do the worksheet, because there's no amount of problems I could do with you together in this video that's going to account for all the different possible interactions that can exist. You really just want to do as many practice problems from this lesson as possible. The other thing you want to do is, like I said before, come up with these lists, okay? If you can find a list of perfect squares, perfect cubes, perfect fourths, perfect fifths, maybe even a few perfect sixths, perfect sevenths, you don't have to get too far because the numbers would get huge, right? But if you can get lists of those numbers and just have them quickly to reference, it's going to make your life so much easier, okay? All right, so just a quick recap. What did we do? We learned the property of exponents and then learned how to use them to solve problems. And then we used the property of radicals also to solve problems. And we had a lot of fun and made a lot of friends along the way. All right, I will see you in the next video.